Okay, so in this video, we are going to see the solution to the Volterra integral equations. Not all Volterra integral equations, but the special type where we have the lower limit of the integral be a constant, mostly zero, and mostly, but it's just a constant. That's what I'm saying. Like, you should get a constant as the lower limit, and the upper limit is going to be a function of x. And in this special type, we have x over here, okay? But it isn't always going to be x. This isn't the only requirement of having a Volterra equation, integral equation. This just should be a function of x. So even if you have x squared plus 3, it's still a function of x. But it's just that we are limiting ourselves to this type, okay? Yeah, so we have to look for the solution to this integral equation. And like I said, if you have the Volterra integral equation, it is always best to apply the Leibniz rule. Okay, the Leibniz rule. That's when you are trying to differentiate the whole thing. You differentiate the whole equation, right? So let's start up. We have the x. Now we are integrating with this. We are differentiating the whole thing with respect to x, because it is only in the integral that you see t, but the actual function is a function of x. Okay, so we are differentiating the whole thing with respect to x. So y of x being equal to f of x plus integral a x k xt y of t t. Okay, so basically you don't see lambda here, but it's actually 1 over here, right? So in cases where you have lambda not being equal to 1, it's just going to apply for the same thing. Actually, I want us to know the steps. Okay, I want us to know the steps in solving this Volterra integral equation. So it is the steps you're looking at, not the final answer alone. Okay, so we have the derivative of y with respect to x being equal to the derivative of f of x with respect to x. Then you have the derivative with respect to x of a x k x t y of t t, and there's your first equation. Okay, so with these ones, it's going to be very easy. This one is just going to be y prime of x. This is going to be f prime of x. So our only problem is with this side. So let's write this somewhere. We have the derivative with respect to x of the integral from a to x k of xt yt dt. And to apply the Leibniz rule, this whole thing is your f of xt. Okay, so in our previous video we got to know that we were integrating a function of x and t, so this whole thing becomes your function of x and t. All right, not only the kernel. All right, so now let's move on. So we know that we are supposed to first have the function at x and the upper limit. Okay, yes, so let me break this one down so that you get to understand it very easily. Let's write these down. Your f of xt is k xt y t. Okay, so in our upper limit we are supposed to get f of x comma x, right? Because we look for f of x at the upper limit and the upper limit, which is x, f of x and the upper limit, which is x over here, and that's going to be equal to k of x, because wherever we see t, it's only t which changed. So wherever we see t, we put in x over here, and here too, we're going to have y of x, right? Yes. Then we check the lower limit as well. So we have f of x and the lower limit a, and that's going to be k of x a y of a. Okay, yes. So now let's rewrite this. We have the derivative with respect to x of the integral from a to x of k of xt y of t dt being equal to f of xx. We know why we are bringing this, because we want the functional value at the x and the upper limit, which is equal to this. So we write that we have k of x y of x minus, then we actually multiply this by the derivative of the upper limits. We multiply this by the derivative of the upper limits, right? So the derivative of x, that's going to be dx dx, okay, yeah, plus that minus, k of x a. Let me shift this a bit on the right. K of x in a, then y of a. We know that's going to be this part, right? It's this part, f of x a, multiplied by the derivative of a with respect to x. That's the lower limit, the derivative of the lower limit. Then plus the integral from a to x of the derivative with respect to x of the whole function of x, which is k of xt yt dt. Okay, yeah. So this becomes the formula. This is the derivative we're looking for. So now let's try simplifying this. We are going to have this being equal to k of x y of x. The x dx gives you 1, so you actually have the same thing, minus, let's look at this value over here. The derivative of a constant alone gives you 0, so it means this whole part is going to 0. So you have minus 0 plus the integral from a to x of del x of k xt y t dt. Okay, so now we can simplify this, and this is going to be equal to k of x y of x minus 0 plus the integral from a to x del x of k of x t y of t dt. Okay, so we can put this whole thing right over here. Okay, so equation 1 then becomes y prime. So this implies that y prime of x is equal to f prime of x plus f prime of x plus the whole of this thing, which gave us plus k of x y of x plus the integral of a to x del x k of x t y of t dt. So this becomes a differential equation. You can see that, because this is always going to give us a function of x. Okay, you're always going to get a function of x over here, because after your differentiation of this with respect to x, you integrate with respect to t. Okay, you integrate with respect to t, then you put in the x values. So this is actually going to be a function of x rather. So in the end, you have a defined integral. It's a definite integral, but this definite integral is going to give us a function of x. So you are going to have a differential equation. Okay, so after solving this differential equation, that becomes the solution to the integral equation. So it means that in solving for the Volterra, or if you're trying to find a solution to the Volterra integral equation over here, what you have to do is to convert this whole thing into a differential equation. Okay, and once you get the differential equation, you solve the differential equation, and that becomes the solution to the integral equation. Okay, yeah. So in our next video, we are going to pick example and we are going to solve them for us to get to know what we're actually doing. So leave a like on the video and subscribe to my channel if you like my content. All right, see ya.